So far, in our study of the method of substitutions, we've only ever been looking at indefinite integrals where there's no bounds. However, we might want to find the area underneath a specific graph on a specific interval. The question is, how do we handle these limits here when we actually are doing the substitution method? Keep in mind that this dx has a very specific meaning and interpretation. It implies that these numbers that we see here, the 0 and the pi over 2, are x-coordinates. In other words, we would be looking at the graph on the x-axis from 0 to pi over 2, and then finding the area underneath this function on that interval. Of course, when we switch to w's, these are not w values, these are x values, and we need to be careful in how we handle those. There are two methods we're going to explore. One is when we actually make the substitution, in other words, we create w equals. What we're going to do is also transform the bounds of the integral, or the limits of the integration, into w's as well. Or another alternative is to keep everything about the limits or the bounds in terms of x, go back to x's before we do our subbing in, and then sub in final x's that we started with into x values and our integral, and keep everything on the up and up by always using the same variable x for the limits and for our function. This all makes more sense through some examples. That's what we'll do next, demonstrating each process with a different integral. Let's show the first method here for converting the bounds of the new variable. So here we have x equals and x equals 0 to x equals pi over 2. We've seen this integral before, and for this integral we chose w equal to cos of x. And we'll quickly recap that. The reason we did cos of x is because the derivative of cos is sine, and that's sitting there as a multiplier, as a factor. We'll go through the process relatively efficiently here and just show the differences. Isolating the dx, -1 over sine of x dw. So our integral is equal to the integral of sine of x is what we started with. We had 1 plus cos squared. But wait, cos of x is w, so we have 1 over w squared. And then the dx value is equal to -1 over sine of x times dw. Now, what about the bounds? Here's where we do the extra step. I like to put them in the same order as they are visually here, vertical on top of each other, this one first, because otherwise I tend to get them mixed up. When converting the limits of integration, I like to write them in the same order as they are visually here. Otherwise, I tend to make silly mistakes and get them backwards. The upper limit is x at pi over 2. However, w is cos of x, so the w value that we're going to get with that is cos of that x value, cos of pi over 2. Cos of pi over 2 is 0. At x equals 0, what's the w? It'll be cos of 0, which is 1. And so that is what we will use as our bounds. And it is going to look odd. In fact, this gets back to an earlier issue about when might we not have an increasing relationship between the first bound and the second bound. A substitution very frequently leads to a large number, then a small number in the bounds of the integral. But that's totally fine. We know how to handle that. If we take the next step in simplifying, we notice the signs cancel. And so we end up with negative the integral from w equals 1. The variables that go with the bounds, if there's any possibility of confusion, because it just reinforces what these values are, what variable they're in terms of. And now we have an integral. If we don't like the 0 and 1 parts though, remember we have that rule that we can swap the limits, swap the bounds, if we flip the sign. So let's do that. just to make it look a little prettier. And now we can integrate. We've seen this integral before. We're going to get the integral of 1 over 1 plus w squared, which is arctan. And we're going to evaluate that between 0 and 1. So last but not least, we're going to have arctan of 1 minus arctan of 0. Perfect. If you wanted to, you could take that a step further. Look up what arctan does again. What angle gives a tan of 1? Well, that's pi over 4. And what angle gives a tan of 0? That's 0. So we'd end up with just pi over 4 as the final value for this quite complicated looking integral that we had at the outset. What was new though was handling this x equals 0 to x equals pi over 2 by turning each of those x values into a corresponding w value. We did that right at the outset, and so we ended up with a new integral all in w's, including the bounds. We're going to see there's another approach that works just as well. It's entirely up to you which one you want to use. If we don't do that step here, but just go back to x's before the end. Let's consider this project here and see how it might work. So here we have a whole pile of square root of x's. Remembering that the derivative of root x, which is x to the 1/2, is going to be x to the negative 1/2, or 1 over root x, and it ends up being a half multiplier. It looks like if we rewrote this with the leading 1 over root x, we'd say, oh, the derivative of root x is sitting in here ready to be canceled. So that's what we're going to use as inspiration for our inside function. If we choose 1 plus root x, I think we're going to get some nice cancellations happening. How do we know? We're never sure until we actually do it. But the process is take the derivative, and we just did a little side calculation there. The derivative of w with respect to x will be 1/2 x to the negative 1/2, or isolating for dx. We'd actually bring things up this time. We'd have 2 root x's times that dw. So, rewriting our integral now, we're going to write it as an integral. The square root of 1 plus root x, well, the inside now is just w. We have a root x on the bottom, we keep that as is. And then the dx in our integral as well gets converted to a 2 root x dw. And as expected, or as hoped anyway, we get the cancellation of the root x's outside. However, we're not done. We had some values here, and because this was a dx, these are implicitly x coordinates. What we're going to do in this approach is keep them as x's by saying they are x's, literally putting x equals. If you wrote this, that would be wrong. Why would it be wrong? Because you've converted to a dw, and if you just wrote this integral without a source, that would mean you had w equals 9 and w equals 64. But w and x are different things. In fact, you could figure out what the w's were. We are just going to avoid that whole issue by being really careful about our notation. This is an integral involving x's. We're going to go back to x's, and once we're there, we'll be able to plug in x equals 64 and x equals 9. We'll just have to keep doing that all the way along, like so. We have a 2 we can bring out, and the expression we have is w to the 1/2. Now we can integrate that. We're going to have 2 times w to the 1/2. When we integrate it, we add 1 to the power, divide by the new power, and we're going to sub in x equals 9. And again, this is explicitly x's, not w's. X equals 9 and x equals 64. Keep going. This will be 4/3. Now we can go back to x's. What was w in our expression? We go back to our very first line where we defined w. It was 1 plus root x. So 1 plus root x to the 3 halves between, x equals 9 and x equals 64. Now everything is in terms of x, including our bounds. Now we can sub in those bounds of the integral, those limits of the integral. And that's going to give us 4/3 times 1 plus the square root of 64 to the 3 halves minus 4/3 1 plus the square root of 9 to the 3 halves. And we could take that a little further if we liked. Though the 3 halves powers are going to be a bit annoying. Let's see how this works out. 4/3, this is 8. Oh, it's actually 1 plus 8 to the 3 halves minus 4/3 1 plus 3 to the 3 halves. That is 9. This actually turns out quite nicely, like a math problem should. 9 to the 3 halves, we have a square root. You can take your calculator and do this if you like, but square root of 9 is 3, and then we cube it, that's 27. Here we have 4, square root of that is 2, and then we cube it, that'll be 8. And if we run all that together, we end up with a nice number, 76/3. Certainly something far nicer than we might have anticipated looking at how complicated the original integral was. Again, what's the takeaway? The substitution happens as normal. The only thing we do to handle the limits of integration, the 9 and the 64 values, is we constantly remind ourselves that these are x coordinates. We didn't change them, we just keep them as x equals 9 and 64 until we finally get to a point where we can sub them in after the integration has been completed. Again, the choice is yours. You can convert these x values to the new variable if you like, or keep them as x's and just go back to x's before you sub them in. Both will give you the same answer in the end.